Something in this universe moves faster than light. Not theoretically, not arguably. Experimentally confirmed, Nobel Prize awarded, every loophole sealed, done. The debate is over. What is not over, what may never be over, is what it means. Because the explanations physicists have come up with range from mildly disturbing to outright reality dissolving. Einstein screamed about this in 1935 and was laughed out of the room. 30 years later, a quiet Irish physicist named Bell handed science the tool to test it. The universe failed the test spectacularly. Tonight we go through exactly what was found, exactly what it breaks, and exactly why the last theory standing should genuinely unsettle you. If you are new here, welcome. Stay until the end, because a rule you were taught was unbreakable turns out to have a crack in it, one the Nobel Committee finally had no choice but to acknowledge. The universe is doing something it is not supposed to be able to do, and it only gets stranger the deeper we go. Now, let us get into it. Part 1. The universe is already breaking its speed limit. Something happened in a laboratory in Delft, Netherlands in 2015 that should have made front-page news around the world. Two particles, photons, the smallest packets of light that exist, were created together, separated, and then measured simultaneously on opposite sides of a building. The moment the first particle was measured and its properties recorded, the second particle instantly snapped into a matching state. Not after a delay, not after a signal travelled across the room. Instantly. Faster than light could have crossed that distance. Faster than any known force in physics could have carried any message. The correlation between the two particles happened in zero time, and no one in that laboratory could explain what mechanism made it possible. What they can say with certainty, is that it happened, and it keeps happening, every single time. This is not a fringe result. This is not a theoretical prediction that physicists argue about in seminars. This is one of the most replicated experimental findings in the history of science, now confirmed by independent laboratories on multiple continents, awarded the highest prize in physics, and accepted as a foundational fact about the universe we live in. The universe produces instantaneous correlations across distance. That is the data. And the reason it should terrify you, not in a science fiction way, but in a deep, unresolved, keeps physicists awake at night kind of way, is that nobody fully understands what is actually making it happen. Let's start with what we actually know, because the facts here are strange enough without adding any drama to them. When two particles are created through the same physical process under the right conditions, they become what physicists call entangled. This is not a metaphor. It is not a poetic way of saying they are related. It means something precise and measurable. The quantum state of each particle cannot be described independently of the other. They share a single quantum description, no matter how far apart they are subsequently moved. You could put one particle in a laboratory in Tokyo and send the other on a spacecraft heading toward Mars, and they would still share that single quantum description. Still be one system, expressed across an enormous stretch of space. Now here is where it gets genuinely strange. Before you measure one of these particles, certain of its properties are not merely unknown, they are genuinely undefined. This is not a limitation of your instruments. Quantum mechanics, in its standard formulation, says that properties like spin orientation simply do not have a definite value until measurement forces them into one. The particle exists in a superposition, a combination of possible states, and measurement is what collapses that superposition into a single outcome. The outcome itself is random. You cannot predict which way it will land. No one can. There is, according to standard quantum theory, no hidden clockwork inside the particle, telling it in advance what result it will give. And here is the part the universe owes you an explanation for. When you measure the first particle, and it randomly lands on one outcome, the second particle, wherever it is, however far away, instantly takes on the corresponding complementary value. Not eventually. Not after a light-speed signal travels between them. The correlation is immediate, experimentally verified to happen faster than any signal travelling at light speed could account for. In some experiments, the two measurement events are separated by distances large enough that light itself could not have travelled between them in the time window of the experiment, and the correlations still hold, every time. The way physicists confirm this is through something called Bell inequality violation, and we'll get into the full mechanics of what that means in a little while. But the short version is this. There is a mathematical ceiling on how strongly correlated two particles can be if they are each just carrying pre-assigned hidden properties and are not in any way influencing each other across distance. That ceiling is a number. Experiments routinely produce correlations that exceed it, not by a little, not by an amount that could be waved away as measurement error, by a statistically overwhelming margin. In the 2015 experiments, the one specifically designed to close every remaining technical objection to the result, the violation was confirmed to a certainty of more than 15 standard deviations. In statistics, 5 standard deviations is considered proof. 15 is so far beyond doubt that the conversation should, rationally, be over, and officially it is. In 2022, the Nobel Prize in Physics was awarded to Alan Aspect, John Clauser and Anton Zeilinger, specifically for their work on entangled photons and Bell inequality violation. The Nobel Committee does not award its higher science prize for controversial or unconfirmed results. What the Nobel Prize meant, in institutional language, is that the physics community has formally accepted that quantum entanglement produces correlations that cannot be explained by any local, classical model of reality. That is as close to an official declaration as science gets. But here is what makes this genuinely maddening rather than just fascinating. None of this allows you to actually send a message faster than light. The correlations are real. The instantaneous matching of distant particles is real. And yet, no matter what you do, you cannot use entanglement to transmit information. This is not a technicality. It is a deep structural feature of how quantum mechanics works, and it is one of the most profoundly confusing aspects of the entire subject. You have two particles that are clearly influencing each other across distance instantaneously, and yet that influence is completely unusable for communication. It is as if the universe built a telephone line between two distant points, then made every message that travels on it pure static that neither party can control or read. That paradox is the actual centre of this story, not the speed, not the weirdness, the paradox. The universe demonstrably does something that looks like it violates the fundamental speed limit of physics, and then refuses to let you take advantage of it in any way that would cause an obvious contradiction with relativity. It's almost like the universe knew someone was going to notice and set up exactly enough cover to technically stay out of trouble. Something is happening, something is crossing that distance, something is coordinating those particles, and whatever it is, we do not understand it. And what is even more unsettling is that this is not a new problem. Someone saw it coming nearly 90 years ago, and nobody listened. Part 2. Einstein's warning nobody took seriously. Albert Einstein was not a man who lost arguments quietly. By 1935, he had already remade physics twice, first with special relativity in 1905, which established that the speed of light was the absolute speed limit of the universe, and then with general relativity a decade later, which redefined gravity as the curvature of space-time itself. He was, without serious competition, the most celebrated physicist in the world, and in 1935 he was deeply, fundamentally troubled by quantum mechanics. Not because he didn't understand it. He understood it very well. He was troubled because he understood it well enough to see what it was quietly implying, and what it was implying horrified him. Together with Boris Podolsky and Nathan Rosen, Einstein published a paper that year laying out what has since become known as the EPR paradox. The argument was elegant and simple. If quantum mechanics is correct that particles in an entangled state share a single quantum description, then measuring one particle in that pair instantly determines something about the other, regardless of how far apart they are. Einstein called this spooky action at a distance, and he meant it as a criticism, not a description to be celebrated. To him, this was a reductio ad absurdum. Either quantum mechanics was incomplete, meaning there were hidden properties the theory wasn't capturing, and the apparent instantaneous influence was just the illusion of ignorance, or quantum mechanics was describing something genuinely non-local, meaning the universe allows influences to propagate faster than light. And Einstein could not accept the second option. His entire framework of relativity was built on the principle that nothing, no information, no influence, no physical effect could travel faster than light. Non-locality would not just complicate his theory, it would undermine the entire logical structure he had spent decades building. What Einstein wanted was a third option: local hidden variables. The idea that particles come with pre-assigned properties set at the moment of their creation, like two gloves shipped in separate packages, where opening one and finding a left glove instantly tells you the other is a right glove, not because of any mysterious influence, but because they were always that way. No instantaneous action required, no non-locality, just information we didn't have yet. That would make quantum mechanics incomplete rather than non-local, and incompleteness, to Einstein, was tolerable. Physics could be fixed and made complete. Non-locality could not be tolerated at all, because it would mean abandoning something more important than any particular theory. The physics community, however, was not in the mood for Einstein's discomfort. The dominant interpretation of quantum mechanics at the time, the Copenhagen interpretation, largely shaped by Niels Bohr, held that asking what particles were doing before measurement was simply not a meaningful question. Quantum mechanics gave you correct predictions. That was enough. Bohr responded to the EPR paper with an argument that most physicists at the time found satisfying, even though, looking back, it was more of a philosophical deflection than a direct refutation. The message from the broader community was unspoken but unmistakable. Einstein was getting old. He was a revolutionary who had become a conservative, uncomfortable with the very kind of conceptual disruption he had once caused. The father of relativity was now the man standing in the way of the next great theory, and so foundational questions about what quantum mechanics actually meant, about whether wave function collapse was a physical process or a mathematical convenience, about whether the universe was truly random at its core or merely appeared to be, were quietly discouraged. A generation of brilliant physicists absorbed the message that asking these questions was unproductive, even embarrassing. The correct approach was to use the formalism, calculate the predictions, and match them to experiment. Shut up and calculate is how the physicist David Mermin later summarized the cultural attitude. Einstein spent the last 2 decades of his career increasingly isolated, continuing to argue that quantum mechanics was missing something, while the rest of the field moved on. He died in 1955 without a resolution. But what neither he nor his critics knew was that the argument he'd made in 1935 had left behind something remarkably useful: an exact map of the contradiction between quantum mechanics and local realism. And about a decade after Einstein's death, a physicist working in near-total obscurity picked up that map and realized it could be tested. Part 3. The forgotten argument that changed everything. John Bell was not famous. In 1964, he was a particle physicist at CERN, working in Geneva on accelerator physics, practical technical work far from the metaphysical debates that had consumed Einstein. But Bell had read the EPR paper. He had absorbed it in a way that most of his colleagues hadn't, with the kind of nagging, refuses-to-let-go dissatisfaction that marks a certain kind of mind. He thought Einstein's concern was legitimate. He also thought Bohr's response had not actually answered it. And unlike Einstein, and unlike the generation of physicists who had grown comfortable dismissing foundational questions, Bell had a talent for making vague philosophical disputes into precise mathematical ones. What Bell did in 1964 was take Einstein's question, does quantum mechanics require non-local influences, or could hidden variables explain everything, and reframe it as a mathematical constraint. He asked, if particles really do have pre-assigned hidden properties set at creation, the way Einstein's local realism demanded, then how correlated can measurements on two separated particles possibly be? And he showed, through careful algebra, that there is a hard ceiling. Under any theory where particles carry pre-existing properties and nothing travels faster than light, the correlations between measurements on two distant particles must satisfy a certain inequality, a specific mathematical boundary that no local realistic theory can exceed. This is Bell's inequality. The genius of the move is its simplicity. Bell didn't need to know what the hidden variables were. He didn't need to know the specific model. He derived a constraint that any possible local hidden variable theory must satisfy, regardless of its details. It was a mathematical shape that the world would have to fit inside if Einstein's view was correct. And then he compared it to what quantum mechanics actually predicted. Quantum mechanics, he showed, predicted correlations that would violate his inequality. The two theories, local realism and quantum mechanics, made different, incompatible predictions about a measurable number, which meant for the first time in the 30 years since EPR, the question was no longer philosophical. It was experimental. You could build an apparatus, create entangled particles, measure their correlations, compute a number, and compare that number to Bell's boundary. If the number stayed below the boundary, Einstein was right. Hidden variables could explain everything. Quantum mechanics was incomplete. If the number exceeded the boundary, local realism failed. Something non-local was happening. The universe was not built the way Einstein demanded it be. Bell had taken an argument about the fundamental nature of reality and turned it into a question with a numerical answer. That is, by any standard, one of the most remarkable intellectual achievements of the 20th century, and it happened in the margins of lunch breaks and spare hours at a particle physics lab in Geneva, published in a journal so obscure that the paper went almost unread for years. What Bell had done, without quite knowing it, was hand physics the exact instrument needed to cut through the fog and measure what the universe was actually doing. And the universe was waiting with an answer that was going to be deeply uncomfortable. Part 4. Bell's inequality, the hidden battlefield of reality. To understand why Bell's inequality is so powerful, you need to sit with a thought experiment for a moment, because the logic here is cleaner than it might first appear. Imagine you and a friend are each handed one glove from a pair of magical gloves. You travel to opposite ends of a city. When you each put on your glove, it randomly turns either red or blue, but the two gloves always turn the same colour. Every single time. 100 out of 100. Now imagine someone asks, are the gloves communicating, or did they just come pre-programmed with the same answer? In that simple case, you cannot tell. Pre-programming explains the result perfectly. No communication needed. Bell's argument is about what happens when you make the test harder. Instead of one question, colour, you give each glove 3 possible questions: colour, texture, and temperature. Each question gets a random yes or no answer, and you ask the same question of both gloves only sometimes, comparing results across many trials where different questions are asked of each. If the gloves are pre-programmed, if they have definite answers to all 3 questions set before you separate them, then when you compare all your results, the number of times you get matching answers follows a predictable mathematical pattern. Bell showed that in a certain set of comparisons, pre-programmed gloves must match at least a certain fraction of the time. That is the inequality. Any local pre-programmed system must satisfy it. No exceptions, no loopholes, no special models that might get around it. The constraint is iron. Now translate this to particles. 2 entangled photons are created and sent in opposite directions. At each end, a detector can be tilted to measure the photon's polarization along one of several different axes. Think of the axis choice as the question being asked. The photons cannot know in advance which axis will be chosen at each detector, because the choice is made after they separate. If both photons were secretly carrying pre-assigned polarization values along every possible axis, the local hidden variable scenario, their measured correlations across many trials would have to satisfy Bell's inequality. They would have to stay inside the mathematical box. Quantum mechanics predicts they won't. It predicts something structurally different, correlations so strong that they exceed what any pre-assignment scheme could produce. The mathematical quantity physicists calculate to check this, often called the S-value in the CHSH version of the inequality, has a classical ceiling of 2. Quantum mechanics predicts S can reach 2 times the square root of 2, which is approximately 2.828. That gap between 2 and 2.828 is not large in absolute terms, but it is the gap between two completely different pictures of reality. One is a universe where particles have hidden, pre-existing properties and no instantaneous influences cross space. The other is a universe where something genuinely non-local is happening, where the outcome at one detector is somehow correlated with the outcome at a distant detector in a way that cannot be explained without accepting that the universe cares about distances in a way local physics doesn't allow. The central thread here is always the same question. Is the universe local, non-local, or built on something deeper? Bell's inequality is the exact instrument that draws the boundary between those possibilities. Everything before Bell was philosophy. Everything after Bell is measurement. And what the measurements would eventually show was not gentle or ambiguous. It was stark, repeated, confirmed, and for anyone paying close attention to what it actually means, still not fully explained. The first time someone actually ran the experiment, the universe started answering. The answer was not reassuring. Part 5. The First Cracks in Reality, 1972 to 1982. John Clauser had read Bell's paper when most of the physics community hadn't bothered. He was a postdoctoral researcher in the early 1970s, working at Berkeley, and he had the distinct and professionally inconvenient conviction that this was the most important unsettled question in physics. He also had, which was rarer and more useful, a plan for how to test it. In 1972, together with Stuart Friedman, Clauser ran the first experimental Bell test. The experiment used pairs of photons emitted from excited calcium atoms, a process called a calcium cascade that produces 2 photons simultaneously, travelling in opposite directions entangled with each other. Polarization filters on each side could be rotated to different angles, corresponding to the different measurement axes in Bell's framework. And across thousands of measurement pairs, the correlations were calculated and compared to Bell's boundary. The result came back on the side of quantum mechanics. The inequality was violated. The correlations exceeded the classical ceiling. It was not a clean, overwhelming result. The statistical significance was real but not enormous, and the experimental setup had imperfections that left room for doubt. But the direction was unmistakable. Local hidden variables were not producing results consistent with the data. Something was already behaving the way quantum mechanics predicted, and local realism did not allow. For Clauser, it was a vindication of a kind. For the broader physics community, it was interesting but not quite convincing, because there were still gaps in the experiment that a determined skeptic could point to. Not with much conviction, but enough. The more important moment came several years later, in a series of experiments carried out in Paris between 1980 and 1982 by a physicist named Alain Aspect. Aspect's experiments were technically superior to Clauser's in several important ways, but the most dramatic improvement was something called dynamic switching. In Aspect's most famous experiment, the measurement settings at each detector, the angle of the polarization filter, were changed randomly while the photons were already in flight. This was crucial, because one of the remaining objections to Clauser's result had been the locality loophole. What if the photons somehow communicated with the detectors before the measurement? What if there was a hidden signal, travelling at or below light speed, that coordinated the results? In Clauser's experiment, the settings were chosen before the photons were released, which left open the theoretical possibility of pre-flight coordination. In Aspect's experiment, the settings were switched after the photons left the source, in a time window short enough that no light speed signal from one detector could reach the other before measurement was complete. The correlations held. The inequality was still violated. The The S value still came in above 2, comfortably above 2, in a way that was statistically significant and experimentally clean enough to seriously narrow the range of objections. Aspect's results caused a genuine shift in how physicists talked about entanglement. You could still find critics, and there were legitimate technical concerns remaining. The detection efficiency of the photon counters was not perfect, which introduced a statistical assumption about whether the photons being detected were representative of all photons being produced, but the trend was obvious. Every time someone improved the experiment and closed a loophole, the result came back the same. The universe kept exceeding Bell's boundary. The classical box kept failing to contain the data. And yet the story was not over, because the remaining loopholes were not just technical complaints. They pointed at something deeper about what kind of universe might be able to explain these results, and closing all of them at once turned out to take another 3 decades. Part 6. The Loophole Problem. Why Nobody Believed It Yet. Science is slow by design, and it is slow for good reasons. The history of physics is littered with results that were exciting, statistically significant, replicated by multiple groups, and wrong. Confirmation bias is not a character flaw unique to lesser minds. It is a structural feature of human reasoning that good experimental design exists specifically to counteract. And so, when physicists in the 1980s and 90s pointed to remaining loopholes in the Bell tests, this was not obstinacy or denial. It was science doing its job. The question was whether those loopholes were genuinely exploitable, whether some realistic alternative explanation of the data actually fit inside them, or whether they were increasingly implausible technical edge cases kept alive only by the discomfort of accepting what the data was saying. The 2 most important loopholes were the detection loophole and the locality loophole. The detection loophole arose from the fact that early experiments could not detect every photon in every pair. Detectors in the 1970s and 80s were not efficient enough to catch more than a small fraction of the entangled photons being produced. The rest were missed. The experiments therefore relied on what is called the fair sampling assumption, the idea that the photons being detected were representative of all the photons being produced. If that assumption was correct, the Bell violation in the detected sample accurately reflected what was happening overall. But if hypothetically some hidden mechanism were preferentially selecting which photons got detected in a way that mimicked a Bell violation without actually being one, the result could be an artifact. This was technically possible. It was also increasingly implausible, because it required an ever more elaborate conspiracy among the photons. But technically possible was enough to keep the argument alive. The locality loophole was the more philosophically interesting one. It asked, what if the measurement settings at the 2 detectors were not truly independent of each other? What if some hidden signal, not necessarily a deliberate one, just some physical correlation built into the experiment, was allowing one side to influence the other in a way that mimicked non-local quantum correlations without actually requiring them? Aspect's time-switching experiment had dramatically constrained this option, but the switching mechanism he used was periodic and somewhat predictable. A sufficiently creative alternative model, using very fast local communication, could theoretically still fit the data. Closing this loophole properly required truly random, unpredictable and fast enough switching that no locally travelling signal could carry information between the detectors within the measurement window. And so, the 1990s and 2000s became a period of incremental refinement. Each new experiment improved on the previous one: better detectors, faster switching, larger separations, more photon pairs. Each new result confirmed the Bell violation, with greater statistical strength and fewer remaining loopholes. But each experiment closed some gaps while leaving others, and the determination to be truly definitive, to run an experiment where every major loophole was closed simultaneously, remained an unfulfilled goal. It required technology that didn't quite exist yet, and it required coordination that was difficult to organize. The question the universe was being asked had not changed since Bell wrote his paper in 1964. The answer kept coming back the same, but physicists wisely, kept demanding better evidence, and then, in 2015, they finally got it. Part 7. The Perfect Bell Tests, 2015. In 2015, 3 independent groups of physicists on different continents simultaneously published loophole-free Bell tests. 3 separate experiments, 3 separate teams, 3 separate technologies, and all 3 closed the major loopholes at the same time for the first time in the history of the subject. The fact that all 3 arrived at the same result should be taken seriously. Independent confirmation at this level is about as close as experimental physics gets to certainty. The most celebrated of the 3 was the Delft experiment, run by Ronald Hansen and his group at Delft University of Technology in the Netherlands. Their approach was different from the photon-based experiments that had dominated the field for decades. Instead of photons, they used the spin states of electrons trapped in nitrogen vacancy centers inside diamond crystals. The 2 diamonds were placed 1.3 kilometers apart, across the Delft University campus, connected by optical fiber. Entanglement between the 2 electron spins was established through an intermediate photon-based protocol, and then the electrons were measured independently at each end. The measurement settings were chosen using quantum random number generators, producing unpredictable choices that were made and applied within nanoseconds, far too fast for any light-speed signal from one side to reach the other before both measurements were complete. This closed the locality loophole. The detection efficiency of the electron spin measurements was high enough to close the detection loophole simultaneously, and the result was a violation of Bell's inequality to a statistical significance of more than 15 standard deviations. At the same time, a group in Vienna led by Anton Zeilinger published a photon-based loophole-free Bell test, using rapidly switched high-efficiency detectors that independently closed both loopholes, and a group in the United States at NIST published yet another version using beryllium ions, with detection efficiencies approaching unity. 3 experiments, 3 technologies, 3 continents, 1 result: local realism fails. The correlations that should be impossible, the correlations that exceed Bell's classical boundary, are exactly what the universe produces, every single time, under conditions where no known classical mechanism can explain them. What the 2015 experiments established was not new in its direction. The direction had been pointing the same way since Clauser in 1972. What they established was finality. The technological limitations that had kept the result controversial were gone. The statistical margins were not borderline, they were overwhelming. The loopholes that creative theorists had used to maintain alternative explanations were systematically sealed. There was no longer a technically honest argument available to a physicist who wanted to defend local hidden variables. The universe had been asked, in the most rigorous conditions ever devised, whether it was behaving locally, and the universe repeatedly, definitively said no. The central question, whether these instantaneous correlations are real and unavoidable, had been answered. What remained was the harder question, the one that doesn't have an experimental answer yet. What is producing them? Part 8. What the Nobel Prize actually admitted. The Nobel Prize in Physics for 2022 went to Alan Aspect, John Clauser, and Anton Zeilinger. The official citation recognized their experiments with entangled photons, establishing violations of Bell inequalities and pioneering quantum information science. If you read only the formal announcement, it sounds technical and contained, like something you would skim past on a science news website between headlines about Mars rovers and new exoplanets. Dry, institutional, precise. The kind of language that makes important things sound boring on purpose. But if you slow down and actually pay attention to what is being said beneath the careful wording, the announcement is anything but boring. It is, in the most understated way imaginable, one of the most consequential scientific acknowledgements of the last 100 years. The Nobel Committee awarded its most prestigious scientific honour, specifically for demonstrating that nature produces correlations that cannot exist in any local, realistic theory of physics. Read that again slowly, because it is easy to let the technical language carry you past what it actually means. A local, realistic theory of physics is not some niche academic model. It is the bedrock assumption that has underpinned physical science since Newton. The idea that objects have definite properties. The idea that what happens here is caused by things here, not by things happening simultaneously on the other side of a building, or a city, or a planet. The idea that influences travel through space and take time to get from one place to another. That is local realism. That is the common sense picture of a universe made of things that exist in places and interact through contact or fields that propagate at finite speeds. And the Nobel Committee, in language carefully chosen to be as undramatic as possible, formally recognized that this picture is wrong, not incomplete, not limited, wrong in a measurable, reproducible, experimentally confirmed way. That is not a minor result dressed up in prize clothing. That is an institutional declaration that the universe does not work the way we thought it did. To understand the weight of what was being honoured, you have to understand how long the road to that podium in Stockholm actually was. It did not begin in a single laboratory on a single morning. It began in 1972 when John Clauser, working at Berkeley with equipment that was impressive for its time and laughably primitive by modern standards, ran the first real experimental test of Bell's inequality using entangled photons produced by excited calcium atoms. Clauser got a result that sided with quantum mechanics over local hidden variables. The correlations were stronger than Bell's classical boundary allowed. The result was real and statistically significant, and almost nobody in the mainstream physics community paid serious attention to it, partly because the experiment had technical limitations, and partly because foundational questions about quantum mechanics were still considered slightly embarrassing to pursue professionally. Clauser did the work anyway, with the particular stubbornness of someone who believes they are asking the right question regardless of whether the field agrees. Then came Aspect in Paris in the early 1980s, with a series of experiments that were technically superior in one crucial and dramatic way. Aspect switched the measurement settings at each detector while the photons were already in flight, closing the door on the possibility that the photons had somehow coordinated their results before separating. The correlations held. The inequality was violated. The S-value came back above 2, comfortably above 2, in a way that was statistically clean and experimentally careful. Aspect's results shifted the conversation. They did not end it, because technical loopholes remained, but they shifted it. The direction was becoming harder to argue with. And then there is Zeilinger, whose contributions span decades, and whose laboratory in Vienna became one of the most productive and inventive in the history of experimental quantum physics. Zeilinger and his group pioneered techniques in quantum teleportation, entanglement swapping, and long-distance entanglement that extended the experimental reach of Bell tests far beyond what earlier generations could manage. His work was part of the broader wave that culminated in the loophole-free Bell tests of 2015, where every major technical objection to the result was addressed simultaneously for the first time. What the Nobel Prize formally recognized was the edifice as a whole, the 50-year experimental program that took Bell's mathematical question and turned it into an experimentally settled fact. The fact being recognized is that quantum entanglement produces correlations that violate Bell's inequality, that the S-value in experiment after experiment persistently exceeds 2, reaching values close to the quantum mechanical prediction of 2.828, and that this cannot be explained by any model in which particles have pre-assigned local properties and influences travel at or below the speed of light. The data is not ambiguous. The conclusion is not soft. Local realism fails. Full stop. But now notice carefully what the Nobel Prize did not say. It did not say that faster-than-light signalling had been observed. It did not say that special relativity had been violated. It did not claim to have identified a physical mechanism for how the non-local correlations were produced. It did not explain what is actually happening inside the particles, or between them, or in whatever structure of reality connects them across distance and zero time. The prize recognized the experimental result. It was silent on the meaning of that result, and that silence was not an oversight. It was a choice, a deliberate, careful, scientifically honest choice. The physics community is extraordinarily precise about the distinction between what is measured and what is understood. What is measured, in this case, is that Bell's inequality is violated, that is confirmed, that is settled. What is not settled, what remains genuinely, profoundly open, is the interpretation. What is actually happening in nature to produce these correlations? What is the mechanism? What is the physical story that connects two particles across space in zero time, without carrying any usable information, without violating relativity in any operational sense, and yet producing correlations that no locally causal model can reproduce? Nobody knows. The Nobel Prize did not answer that question, because no one has answered that question. The careful wording of the prize reflects a scientific conservatism that is genuinely important here, not bureaucratic timidity. It reflects the honest position of a field that knows exactly what it has measured and is not yet willing to claim it knows what that measurement means. And the gap between those two things, between the certainty of the experimental result and the complete absence of a consensus on its meaning, is exactly where the most consequential, most philosophically explosive, most unresolved questions in modern physics currently live. This is not a gap that will be closed by a better detector or a larger sample size. It is a conceptual gap. A gap in the story physics tells about what reality actually is. The correlations are fact. They happen. They are measured. They are confirmed. Their meaning is still, in a genuinely deep sense, wide open. And the options physicists have developed for filling that gap, the interpretations that attempt to explain what the universe is actually doing when two distant particles snap into correlated states in zero time, are not comfortable. They are not reassuring. They do not resolve into a picture that looks like anything you were taught to expect from a sensible, well-ordered physical universe. They are strange in ways that go all the way down, and that is exactly where we are headed next. Part 9. The communication paradox. Here is the thing that will make your head hurt if you sit with it long enough. The correlations are instantaneous. They are non-local. They exceed what any locally causal model of the universe can produce. And you cannot use any of this to send a message, not because the technology is not good enough yet, not because physicists have not figured out the right trick or built the right device, not because the experiment needs another decade of refinement, because of something deep and structural about how quantum mechanics is built, something baked into the mathematical foundations of the theory itself, present from the beginning, and showing no signs of yielding to cleverness or persistence or better equipment. The door is not locked because we lost the key. The door does not exist. To understand why, you have to understand what actually happens when you measure one particle from an entangled pair. You set up your detector. You choose your measurement axis. You press the button, metaphorically speaking, and you get a result. Spin up or spin down, polarization horizontal or vertical. Whatever the specific property being measured, the outcome comes back as one of two options. And here is the part that matters. You did not choose that outcome. You chose the question. The universe chose the answer. The result is fundamentally random, not random in the way a coin flip is random, where the outcome is determined by physical forces you could theoretically calculate if you knew enough. Random in a deeper sense. Random in the sense that quantum mechanics, in its standard formulation, says there is no prior fact of the matter about which way the result will land. The universe is not hiding the answer from you. There is no answer until measurement creates one. And the specific answer that gets created is not under your control in any way that current physics can identify, or that any experiment has ever suggested might be accessible. This is the wall that blocks faster-than-light communication using entanglement. Because you cannot control the outcome on your end, you cannot encode information into it. You cannot decide to send a sequence of spin up, spin up, spin down, spin up that spells out a message in some agreed code. You get whatever the universe gives you, in whatever order the universe chooses, and that order is noise. Pure, structureless, random noise. a sequence that carries no information because no one chose it. Now consider what the person on the other end of the entangled pair sees. They are measuring their particle far away, simultaneously, or close enough to simultaneously, that no light-speed signal could connect the two events. They get results too, spin up or spin down in some sequence, and their sequence, like yours, looks like pure noise, random, unstructured, carrying no detectable pattern. If you handed their sequence of results to the most sophisticated pattern recognition system ever built, it would find nothing. No signal, no message, no trace of anything other than randomness doing what randomness does. And yet, and this is the part that makes the whole thing so maddening, if you and the distant experimenter get on a phone call afterward, a regular old classical phone call travelling at the speed of light or slower, and you compare your sequences of results, something extraordinary emerges. The correlations between your sequences are stronger than any classical model allows. The matches, in the specific cases where you made corresponding measurement choices, exceed Bell's boundary by the margin that has now been confirmed in hundreds of experiments across 50 years of physics. The entanglement was real. The non-local connection was real. The instantaneous coordination of your results and theirs was real. It was happening the entire time. You just could not see it until you compared notes through a channel that travels at ordinary speeds. This is the structure of the no-signalling theorem, and it is worth sitting with because it is genuinely one of the most peculiar arrangements in all of known physics. The theorem is not an experimental finding that could be overturned by a better measurement. It is a mathematical proof, derived directly from the formalism of quantum mechanics, that says no matter what you do, no matter how you manipulate the entangled particles, no matter what sequence of quantum operations you perform before measurement, no matter how cleverly you design the protocol, no information about choices made on one side can reach the other side faster than light. The randomness is not a bug in the system. It is the lock on the door. The very feature of quantum measurement that makes the outcomes unpredictable is the same feature that makes those outcomes useless as a communication channel. The universe has, with a precision that feels almost architectural in its deliberateness, arranged things so that the non-local correlations are perfectly real and completely unusable. Think about what this means for a moment. You have two particles that are clearly, demonstrably, experimentally confirming that something is connecting them across space in zero time. Something is coordinating their outcomes. Something is ensuring that when one goes up, the other responds in the corresponding way, instantaneously, regardless of how far apart they are, regardless of what barriers or distances or time constraints separate the measurement events. That something is real. It is not a mathematical abstraction. It is not an artifact of how we are choosing to describe the situation. It is producing measurable effects in the data that violate the mathematical ceiling imposed by local realism. It is there, and you cannot touch it. You cannot use it. You cannot point to it. You cannot build anything with it. You can only measure its footprint in the statistics and know that something is happening that you do not have a physical story for. It is, honestly, one of the most exquisitely frustrating structures in the history of science. The universe appears to be doing something non-local right in front of you in the most explicit and measurable way imaginable. And it has engineered the situation, or the situation has emerged from its deepest mathematical structure, with such precise elegance that you cannot leverage it, exploit it, weaponize it, or build anything with it that would produce an observable contradiction with special relativity. Relativity survives, not because nothing non-local is happening, but because whatever is happening non-locally is wrapped so completely in irreducible randomness that it cannot carry a message. The shield and the phenomenon arrive together, inseparable, as if the theory knew someone was going to look for a loophole and closed it from the inside. Physicists call this non-local, but non-communicative, which is a phrase that sounds almost reasonable until you think about it carefully. Non-local means the correlations cannot be explained by anything travelling between the particles at or below light speed. Non-communicative means you cannot use those correlations to send a signal. Both of those things are true simultaneously. The universe is doing something faster than light, and has made it completely useless for the one application that would make the faster-than-light nature of it impossible to ignore. The correlations exist in the data. The mechanism that produces them is invisible to every instrument we have built. The channel is open and carries nothing you can read without a classical connection to decode it. And somewhere underneath all of this, underneath the randomness and the correlations and the theorems and the Nobel Prize and the 50 years of increasingly precise experiments, something is connecting those particles. Something spans that distance in no time at all. We do not know what it is. We do not have a physical picture of it. We do not have a theory that explains it in mechanical terms that would satisfy someone who wants to know not just what happens, but why. And that gap between what we can measure and what we can explain is not closing. It is, if anything, getting more precisely defined. Which is its own kind of unsettling, because a mystery with sharp edges is harder to dismiss than a mystery with blurry ones, and this one has very sharp edges indeed. Part 10. The Collapse Problem, Copenhagen Crisis. To understand why physicists find this so uncomfortable, you need to understand what quantum mechanics actually says happens during a measurement. Not the popular science version, not the version that gets smoothed out for a general audience and arrives scrubbed of its stranger implications. The actual version. The one sitting in the textbooks that every physics student works through, the one that underlies virtually every quantum mechanical calculation ever performed, the one that has produced the most precisely verified predictions in the history of science. Because that version, when you read it carefully, contains something that nobody has fully resolved. Not in the 1920s when the theory was first assembled. Not in the decades of extraordinary experimental success that followed. Not today. The formalism works. The interpretation is, depending on who you ask, anywhere from incomplete to quietly catastrophic. Here is what the standard formulation actually says. A particle, before it is measured, exists in what is called a superposition of possible states. This is not a poetic way of saying we do not know which state it is in. It is a precise mathematical statement that the particle does not have a definite value for certain properties at all. It has a quantum state, a wave function, that encodes the probabilities of different outcomes if a measurement were to be made. The particle is not secretly spin up, waiting for you to discover it. It is genuinely, physically, in a combination of spin up and spin down simultaneously, in a way that has real measurable consequences for how it behaves. Experiments testing quantum interference confirm this. The superposition is not ignorance. It is a description of how the particle actually is. Then you measure it, and something happens that the theory describes but does not explain. The wave function collapses. The superposition, the spread of possible states, each with its associated probability, instantly resolves into a single definite outcome. You get spin up or spin down. One answer, the other possibilities vanish, and they do so not gradually, not through some physical process that takes time and leaves a traceable signature, and can be described in terms of forces or fields or interactions, instantaneously. The collapse, in the standard formulation, is not a physical event with a duration and a mechanism. It is a mathematical discontinuity, a jump from many possible states to one actual state, happening in no time, with no specified cause, triggered by something called measurement that the theory itself never precisely defines. For a single particle measured in isolation, this is already philosophically uncomfortable in ways that are easy to underestimate if you have not sat with them. Where does the collapse happen? At the detector, in the experimenter's brain, at some threshold of interaction between the quantum system and its environment that nobody has drawn a precise line around. What counts as a measurement in the first place? Is a photon hitting a crystal a measurement? Is an electron scattering off another electron a measurement? Does a measurement require a conscious observer, which is an idea that sounds mystical but was taken seriously by some of the founders of the theory? Or does it just require a sufficiently large and complex environment which pushes the problem back a level without actually solving it? These questions have been asked since the 1920s. They do not have agreed answers. The Copenhagen interpretation, which remains the dominant framework in physics education and the one most working physicists fall back on when pressed, handles this discomfort through a move that is either deeply wise or deeply evasive depending on your philosophical temperament. It simply declines to answer. In the Copenhagen view, the wave function is a calculational tool. It is a device for computing the probabilities of measurement outcomes. It gives you the right numbers. That is what it is for. Asking what the wave function really is, whether it represents something physically real that actually collapses when measurement occurs, or whether it is merely a summary of an observer's knowledge about a system, just is, in the Copenhagen view, a category error. You're asking physics to answer a question that physics is not in the business of answering. Physics predicts what you will observe when you measure. It does not describe what is happening when no one is looking. The question of what the particle is doing between measurements is, from this perspective, not a scientific question at all. It is a metaphysical indulgence. For many physicists, particularly those focused on practical calculation and experimental prediction, this is a perfectly satisfying position. The theory works. The predictions are correct. The experiments confirm the numbers to extraordinary precision. Why demand more than that? Why insist on a mechanical story underneath the formalism when the formalism already delivers everything experimentally accessible? This attitude, pragmatic, productive, and deliberately incurious about foundations, dominated physics for decades and produced an enormous amount of genuinely important science. It is not an unreasonable position. It just has a cost that becomes visible the moment you stop looking at single particles in isolation and start looking at entangled systems. Because in an entangled system, the evasion that Copenhagen pulls off for a single particle becomes spectacularly, uncomfortably expensive. When you measure one particle of an entangled pair, you're not just collapsing the wave function of that one particle. You're collapsing the quantum state of the entire two-particle system. The two particles do not have independent wave functions once they are entangled. They share a single quantum state, one mathematical object that describes both of them together, regardless of the physical distance between them. When measurement forces that shared state to collapse, both particles resolve into definite values simultaneously, not sequentially, not with one collapse travelling to the other at some speed, simultaneously, instantaneously, wherever they are. Now you face a fork in the road, and both paths lead somewhere uncomfortable. If you believe that wave function collapse is a real physical event, that something actually happens in nature when a measurement is made, that the collapse is not just a mathematical update, but a genuine physical transition, then you have just accepted that a real, physical event is happening instantaneously across whatever distance separates the two particles. That is a non-local physical event. Something real is propagating across space faster than light. You cannot avoid that conclusion if you take collapse seriously as a physical process. You have accepted non-locality into your picture of the world, and you have to deal with what that means for everything else you believe about how physics works. If, on the other hand, you take the Copenhagen position that collapse is not a physical event at all, that it is merely an update to a probabilistic description, a revision of our knowledge rather than a change in nature, then you sidestep the non-locality problem. Nothing physical propagated across space. Nothing real happened instantaneously. You just updated your probability bookkeeping, clean, local, relativity-friendly. Except now you have surrendered something important. You have given up any right to ask what the particle was doing before you measured it. You have given up any claim to explain what caused the specific outcome you got, rather than the other possible outcome. You have given up the ability to say what the universe chose and why. The calculation is preserved. The story is gone. You get the numbers but not the narrative, the predictions but not the physics, the what but not the how or the why. For a theory that is supposed to be describing physical reality, that is a significant thing to walk away from. Both options are uncomfortable. Both options leave something essential unresolved. And the discomfort is not a personality quirk of particularly philosophical physicists who have too much time to think. It points at something genuinely absent from the theory. Quantum mechanics, in its standard form, does not tell us what is happening. It tells us what to predict. It is extraordinarily good at the predicting. It may be the single most successful predictive framework in the history of human thought. But prediction and explanation are not the same thing, and the gap between them, the gap between knowing what the measurement will show and knowing what is actually happening in nature to produce that measurement, is a gap that quantum mechanics has carried inside it since the beginning. For a long time, that gap was treated as a feature rather than a bug, a sign of appropriate scientific humility rather than an unfinished foundation. But the Bell experiments changed the stakes, because now the gap is not just a philosophical preference about how much explanation physics owes us. Now the gap sits directly on top of the most experimentally confirmed and least understood phenomenon in modern physics. The correlations are real, the mechanism is absent, and the theory that predicts the correlations perfectly is also the theory that declines, structurally and deliberately, to tell us what is producing them. That is the crisis, and it is not going away. Part 11. Many worlds. No collapse, no signal. If wave function collapse is the source of the non-locality problem, one obvious response is to get rid of collapse entirely. It sounds almost too simple when you put it that way. The thing causing the problem is collapse, so remove collapse and the problem goes away. Clean, surgical, decisive, and in a narrow technical sense, it works. The non-locality that haunts the Copenhagen interpretation, the instantaneous physical event propagating across space when a measurement is made, simply does not exist in a framework where collapse never happens. You cannot have a non-local collapse if there is no collapse. The math is preserved. The predictions are identical. The experimental results are reproduced exactly. And the price you pay for this elegant solution is something so staggering in its implications that many physicists who encounter it for the first time genuinely cannot decide whether to find it liberating or deeply, fundamentally disturbing. This is, stripped of its elaborate philosophical architecture, exactly what the many worlds interpretation of quantum mechanics does. Hugh Everett was a graduate student at Princeton in the mid-1950s when he developed the idea, working under the physicist John Wheeler, who was himself one of the more adventurous conceptual thinkers in 20th century physics. Everett's proposal, published in 1957, started from a deceptively simple observation. The wave function, in standard quantum mechanics, evolves according to a precise equation, the Schrödinger equation that is perfectly deterministic, perfectly smooth, and produces no collapse whatsoever. Left to itself, a quantum system just evolves. The superposition grows, spreads, becomes more complex but never jumps, never discontinuously resolves, never does anything as abrupt and unexplained as collapsing into a single outcome. Collapse in the standard formulation is something that gets added on top of the smooth evolution, invoked at the moment of measurement, with no derivation from the underlying equations and no precise specification of when or how it occurs. Everett's question was simple and radical. What if we just took the equation seriously? What if the wave function always does exactly what the Schrödinger equation says, with no collapse, no exception, no additional postulate bolted on at measurement time? What would that actually look like? What it looks like, Everett showed, is branching. When a measurement is made and the outcome appears to resolve into a single definite result, what is actually happening in the many worlds picture is that the universe splits. All possible outcomes occur simultaneously, each in its own branch of reality. The particle does not collapse to spin up. Instead, a branch of reality exists in which the particle is spin up and the experimenter measured spin up, and everything that subsequently interacts with that experimenter becomes consistent with a spin up result. And simultaneously, another branch of reality exists in which the particle is spin down and the experimenter measured spin down, and everything downstream of that measurement is consistent with spin down. Both branches are equally real. Both experimenters, in their respective branches, have a perfectly ordinary experience of measuring a particle and getting a single definite result. Neither of them experiences a split. Neither of them is aware of the other branch. From inside each branch, the world looks exactly like it would look if collapse had occurred. But no collapse happened. The wave function is still there, still complete, still containing both outcomes. Nothing was discarded. Everything is happening simultaneously in branches that no longer interact with each other. The appeal of this from the perspective of the non-locality problem is immediate and genuine. If there is no collapse, there is no instantaneous physical event propagating across space when you measure one particle of an entangled pair. What happens instead is a branching. Your local interaction with your particle causes a local branching of reality, in which you in one branch measured spin up and you in another branch measured spin down. The distant particle, wherever it is described by a wave function that is correlated with yours. When the branching occurs on your end, the correlations are preserved across the branches without anything travelling between the particles. In the branch where you measured spin up, the distant particle's state is consistently correlated with spin up. In the branch where you measured spin down, it is consistently correlated with spin down. But this correlation is a structural feature of the branching, not the result of any influence travelling between the two particles. Non-locality disappears. Relativity is intact. No hidden mechanism required. No instantaneous signal crossing space. Just the smooth, deterministic, local evolution of a wave function that contains everything. It is a genuinely elegant solution to the non-locality problem, and it would be intellectually dishonest not to acknowledge that. Many serious physicists, not fringe thinkers, not people looking for an excuse to believe in parallel universes, but careful, technically sophisticated researchers who have examined the interpretational landscape carefully, consider many worlds the most mathematically natural and philosophically coherent framework for quantum mechanics. It takes the equations at face value. It adds no extra postulates. It produces no measurement problem in the standard sense because measurement is just a physical interaction described by the same equations as everything else. It is, in a technical sense, the minimal interpretation, the one that requires the fewest additional assumptions beyond the bare formalism. The cost, of course, is everything else, and everything else is not a small thing. The many worlds interpretation requires the literal physical existence of an uncountably enormous number of parallel reality branches constantly multiplying with every quantum event everywhere in the universe, every radioactive decay that could have gone either way, every photon that could have been reflected or transmitted, every electron spin that could have resolved up or down, every quantum event at every scale, in every particle, in every atom, in every cubic centimetre of space, throughout the entire history of the universe and into its future. Each of those events branches reality. Each branch then contains further events, each of which branches again. The resulting structure is not just large, it is not just difficult to visualize, it is a multiplicity of complete, fully realized realities so enormous in number that no mathematical language comfortable to human intuition can adequately represent it. And every single one of those branches is, in the many worlds picture, equally real, equally physical, equally present in the universe, even though we in our particular branch have no access to any of the others and no way to confirm their existence. This is not a small ontological price tag. When philosophers talk about ontological economy, the principle that a theory should not multiply entities beyond necessity, they mean something like this. You have solved the problem of non-local collapse by replacing it with infinite parallel realities. Whether that trade is worth making is genuinely a matter of reasonable disagreement among serious people. Some physicists find the many worlds picture clarifying and even beautiful, a universe that is bigger and stranger than we imagined, but internally consistent and mathematically clean. Others find it so extravagant in its commitments, so wildly in excess of anything that could ever be directly confirmed, that accepting it feels less like scientific reasoning and more like a philosophical choice made on aesthetic grounds. And beyond the ontological extravagance, there are serious technical problems within the interpretation itself that have not been fully resolved. The most persistent and important is the question of probability. In a universe where all outcomes happen, where every branch is real, why do some outcomes happen with probability 1/3 and others with probability 2/3? Where do the probabilities come from? The Born rule, which is the formula quantum mechanics uses to calculate the probability of a particular measurement outcome, is simply postulated in the standard formulation. You compute the square of the wave function amplitude and that gives you the probability. It works. It matches every experiment ever performed. But in the many worlds framework, where every outcome happens in some branch, the notion of probability becomes conceptually slippery. If spin-up happens in one branch and spin-down happens in another branch, and both branches are equally real, in what sense is spin-up more probable than spin-down? What does it even mean to say that one outcome is more likely than another in a universe where both definitely occur? Various answers have been proposed, some of them technically sophisticated and genuinely interesting, involving ideas about the relative measure of branches or decision-theoretic arguments about how a rational agent should bet across branches. None of them has achieved consensus. The Born rule, in the many worlds picture, remains something that needs to be derived or justified rather than simply postulated, and the derivations that have been offered remain contested. It is a real problem, not a peripheral one, because if you cannot recover the correct probabilities from your interpretation, you have not actually reproduced quantum mechanics. You have reproduced a theory that says all outcomes happen without a satisfying account of why some outcomes seem more likely than others from inside any given branch. The many worlds interpretation trades the mystery of non-local collapse for the mystery of why probability works the way it does in a universe where everything happens. Whether that is a good trade depends entirely on which mystery you find more tolerable. And the central question, what is making those distant particles correlate in the way the experiments confirm, gets answered by many worlds with the word structure rather than signal. The correlations are built into the branching geometry of the wave function. Nothing travels, everything branches. The universe is simply larger, in a very specific and very strange sense than we assumed. Whether that answer satisfies you is, at this point, a matter between you and your philosophical intuitions. And if it does not satisfy you, there is another interpretation waiting that takes the opposite approach entirely, one that does not eliminate non-locality, but instead looks it directly in the eye and decides to make it the foundation. Part 12. Bohmian Mechanics. Accept non-locality directly. David Bohm took the opposite path. Where Copenhagen avoided the question of what is happening underneath the formalism, and where many worlds dissolved the problem by multiplying reality into infinite branches, Bohm did something that required a particular kind of intellectual courage. He looked directly at what the experiments were implying, accepted it without flinching, and built a theory around it. The result was a framework that is, depending on your perspective, either the most honest interpretation of quantum mechanics ever constructed or the most uncomfortable one, possibly both simultaneously. To understand what Bohm did, you need to go back to a picture of quantum mechanics that predates the Copenhagen interpretation, a picture that was actually present at the very birth of the theory, and then quietly abandoned under pressure from the dominant figures of the field. In 1926, just as quantum mechanics was being assembled into its modern form, the French physicist Louis de Broglie proposed something called the pilot wave theory. The idea was straightforward in its structure, even if strange in its implications. Particles are real. They have definite positions at all times. They are not smeared out into superpositions. They are not indefinite. They are exactly where they are, moving along precise trajectories the way classical physics always assumed. But they are not moving freely. They are being guided, piloted, by a wave. A real physical wave that fills space, evolves according to the Schrödinger equation, and choreographs the motion of every particle it touches. The wave and the particle are both real. The wave does not represent the particle, it guides it. De Broglie presented this idea at the Solvay Conference in 1927, one of the most consequential gatherings in the history of physics, and it was not well received. The Copenhagen framework, championed by Bohr and supported by the enormous intellectual authority of Werner Heisenberg and others, was already consolidating its dominance. The prevailing mood was that asking about particle trajectories between measurements was the wrong kind of question, metaphysically naive, scientifically unnecessary. De Broglie's pilot wave was dismissed, and he eventually abandoned it himself. The idea went dormant for 25 years, until David Bohm, working in Princeton in the early 1950s, independently rediscovered and dramatically extended it. Bohm's version, published in 1952 in 2 papers in Physical Review, was technically complete in a way that de Broglie's original sketch had not been. Bohm showed that you could construct a fully consistent formulation of quantum mechanics in which particles always have definite positions, always move along definite trajectories, and are guided through space by a real physical field he called the quantum potential, derived from the wave function. The apparent randomness of quantum measurements, the fact that you cannot predict whether a particle will be measured spin up or spin down, arises not from any fundamental indeterminism in nature, but from ignorance of initial conditions. The particle has a definite position. You do not know what it is. Average over your ignorance of those initial positions in the right way, and you recover exactly the probabilistic predictions of standard quantum mechanics. Every experiment, every number, every statistical distribution reproduced perfectly from a theory in which nothing is fundamentally random and particles are always exactly where they are. This is worth pausing on because it is a remarkable fact that tends to get lost in the sociological history of why Bohmian mechanics is not more widely taught. The 2 theories, standard quantum mechanics with its wave function collapse and measurement postulates, and Bohmian mechanics with its definite particle trajectories and pilot wave, make identical predictions for every experiment that has ever been performed or that can currently be conceived. There is no measurement, no observation, no statistical test that distinguishes them. They are observationally equivalent, which means that the choice between them is not at present an empirical question. It is a question about what kind of physical story you're willing to accept underneath the mathematics. And Bohm's story, whatever its other properties, has one feature that Copenhagen and many worlds both lack. It tells you, at every moment, where the particles are and how they are moving. It has a narrative, it has a mechanism, it has, in the most basic sense, a picture of what is happening. The price of that picture is non-locality, stated explicitly and without apology. This is the feature of Bohmian mechanics that makes many physicists uncomfortable, even though, and this is crucial, it is the same non-locality that the Bell experiments have already confirmed is present in nature, regardless of interpretation. The guidance equation that tells each particle how to move depends on the wave function of the entire system, not just the local wave function in the particle's immediate vicinity. The global wave function, the one that encodes the state of every particle entangled with it, no matter where those particles are, no matter how far they have travelled from each other since their entanglement was established. When something happens to a distant entangled particle, when it is measured, when it interacts with something, the wave function of the entire system changes instantaneously, and that instantaneous change propagates instantly through the guidance equation to affect the motion of every other particle in the entangled system. There is no delay. There is no signal travelling between them at light speed. The influence is instantaneous, global, and built directly into the structure of the theory. Bohm did not hide this. He did not use careful language to make it sound less stark than it is. The non-locality is there, in the equations, explicit and unambiguous. And John Bell, after publishing his famous theorem, found this honesty deeply appealing. Bell was, by his own account, motivated to work on the foundations of quantum mechanics, partly by his encounter with Bohmian mechanics, which showed him that a deterministic, realist theory of quantum phenomena was mathematically possible. that the Copenhagen Declaration of Fundamental Indeterminism was a philosophical choice, not a logical necessity forced by the mathematics. Bell became one of the most vocal advocates for taking Bohmian mechanics seriously, not necessarily as the final word on quantum foundations, but as a proof of concept that realist, deterministic quantum theories were coherent and complete. If the Bell experiments show non-local correlations, Bell argued, then a physically honest theory should contain non-locality directly and openly, rather than concealing it behind formalism that technically implies non-locality without ever saying so out loud. Bohmian mechanics, in Bell's view, had the intellectual honesty to say what the data was already saying. The universe is non-local, and we should build our theories accordingly. The reason Bohmian mechanics is not the dominant interpretation in physics today is a mixture of the sociological and the technical, and it is worth being clear about both. The sociological part is real and should be acknowledged. Bohm's papers arrived in 1952, when the Copenhagen interpretation had already been the standard framework for a generation of physicists. Bohm himself was a politically controversial figure. He had been called before the House Un-American Activities Committee and was forced to leave the United States, spending much of his career in Brazil and then Britain, outside the main centres of American and European physics. His theory had the conceptual smell of hidden variables about it, which had been declared dead by the Copenhagen establishment, even though Bohm's hidden variables were of a completely different character than the ones Bell's theorem rules out. The professional and social winds were against it from the beginning, and physics, like all human enterprises, is not immune to fashion and authority. But the technical concern is also genuine and should not be dismissed. Bohmian mechanics works with remarkable elegance for non-relativistic quantum mechanics, for particles moving at speeds well below light speed, described by the ordinary Schrödinger equation. Extending it to relativistic quantum field theory, the framework that describes particles moving near the speed of light and governs the behaviour of fundamental fields, has proven genuinely difficult. The non-locality that the theory embraces explicitly turns out to be technically challenging to reconcile with the mathematical structure of special relativity, which requires that the laws of physics look the same in all reference frames moving at constant velocity relative to each other. A theory with instantaneous non-local influences has to handle this requirement with great care, and while Bohmian approaches to relativistic field theory exist and are actively developed by a community of researchers, none of them has achieved the clean, complete, universally accepted form that non-relativistic Bohmian mechanics enjoys. The theory is not finished in its most general form. That is a real limitation. And yet the universe, in the Bohmian picture, is something almost majestic in its strangeness. It is a universe saturated with instantaneous non-local connection, every particle continuously guided by a wave function that knows about the entire system it belongs to, no matter how spread across space that system has become. The correlations that Bell tests measure, those persistent, loophole-free, Nobel Prize-confirmed violations of local realism, are not mysterious in this picture. They are not paradoxes requiring interpretation or philosophical gymnastics to accommodate. They are the direct, visible signature of a universe that is fundamentally, constitutively, non-locally connected. The entangled particles are not communicating faster than light in any sense that violates relativity operationally, but they are part of a single system described by a single wave function that responds as a whole to what happens to any part of it. The non-locality is not a bug the theory has to explain away. It is the mechanism. It is the answer. It is what the universe is actually doing, stated plainly, without evasion. Whether that makes Bohmian mechanics more honest or more disturbing is a question that different physicists answer differently, and the honest answer is probably that it is both. It is more honest because it says out loud what the data implies. It is more disturbing because what the data implies, stated out loud without softening, is that the universe is connected across all distances instantaneously through a real physical field that no instrument has ever directly detected and that no one fully understands. The wave function in Bohm's picture, is not a calculation tool. It is a real thing. It fills all of space. It knows about everything, and it is guiding every particle in existence along paths that are determined, continuous, and shaped by the entire non-local structure of reality at every moment. That is either the most complete picture of nature that quantum mechanics has yet produced, or it is the most unsettling. Quite possibly it is both at once. And if you thought that was the strangest option on the table, there is one more interpretation waiting, one that does not just accept non-locality or eliminate collapse or multiply branches, one that questions whether the experiments themselves are telling us what we think they are, and it is the one that makes physicists the most uncomfortable of all. Part 13, Superdeterminism, the Forbidden Escape. At the centre of every Bell test ever performed, including the most advanced loophole-free experiments completed in 2015, there is a quiet assumption so foundational that it rarely gets mentioned outside specialist discussions. Yet, if this assumption fails, the entire argument for something faster than light doesn't just weaken, it collapses completely. That assumption is called measurement independence, sometimes referred to as the free choice assumption, and it is the hidden hinge on which the entire Bell argument swings. To see why this matters, imagine a Bell test like a carefully staged cosmic coin experiment. Two entangled particles are created and sent far apart, sometimes across kilometers, sometimes through fiber networks, sometimes even between satellites and ground stations. At each end, an experimenter chooses how to measure the particle, which question to ask it. Those choices are not just procedural details. The entire test depends on them being genuinely independent. Bell's inequality assumes something very specific. The properties of the particles, whatever hidden variables they might carry, are statistically independent of the measurement settings chosen later. In simpler terms, the particle does not know in advance what you're going to measure, and your choice of measurement is not secretly coordinated with the particle's hidden state. That separation is what makes the test meaningful. Bell's inequality is derived under assumptions that include locality, realism, and measurement independence. When those hold, the math produces a strict boundary on how strongly two particles can be correlated if only local hidden variables are involved. Quantum mechanics violates that boundary repeatedly and with high precision, which is why physicists say nature is non-local. But here is where things become fragile. If measurement independence is removed, the inequality itself no longer holds. The derivation quietly depends on probability rules that assume you can factor reality into independent pieces. What exists in the particle system, and what is freely chosen in the measurement setup. Break that separation, and the inequality loses its force entirely. It becomes like trying to test fairness in a game where the dice and the rules were secretly designed together from the start. This opens a disturbing possibility. If even a subtle correlation exists between the hidden properties of the particles and the so-called random choices made by experimenters, then Bell test violations could appear even if the universe is fully local and deterministic. Not because quantum mechanics is wrong, but because the experiment is no longer independent of what it is testing. The result would mimic non-locality perfectly, while hiding a deeper coordinated structure. This idea has a name: superdeterminism. It proposes that the universe is fully deterministic, and that all correlations, including those between human measurement choices and particle states, are fixed by the initial conditions of the cosmos. In that picture, when scientists think they are freely choosing measurement settings using random number generators, cosmic noise, or quantum randomness, those choices were never truly independent. They were always part of the same causal chain that produced the particles being measured. From this perspective, Bell violations are not evidence of faster-than-light influence at all. They are the natural outcome of a universe whose initial conditions already encode correlations between everything that will ever interact. Nothing needs to travel between distant particles in real time. Everything is already synchronized from the beginning. This is where the idea becomes unsettling for most physicists. Superdeterminism is not rejected because it violates a known law of physics. It does not. It is rejected because it attacks the foundation of experimental science itself. If measurement choices are never truly independent, then the concept of a controlled experiment begins to lose meaning. Science depends on the assumption that we can vary conditions freely and observe how nature responds. Superdeterminism removes that independence, suggesting that every choice is part of a pre-existing structure that also includes the system being tested. In its most extreme form, this leads to a disturbing implication. The universe has been arranged from the beginning so that every Bell experiment ever performed will always produce results that look like non-locality, regardless of what settings are chosen. It is not a conspiracy in the intentional sense, but it can feel indistinguishable from one. Every attempt to test the system is already embedded in the system itself. This is why many physicists describe the idea as deeply uncomfortable. It is not that it is mathematically inconsistent or forbidden by known physics. The discomfort comes from what it implies about independence, causality, and even the meaning of scientific inquiry. If every experiment is pre-correlated with its outcome, then no experiment can ever fully step outside the system it is probing. Yet some physicists argue that discomfort is not a valid scientific objection. Sabine Hossenfelder, among others, has suggested that superdeterminism deserves more serious consideration precisely because it is not ruled out by experiment. From this perspective, rejecting it because it feels conspiratorial or philosophically troubling is not the same as disproving it. The universe, after all, is not required to match human intuition about freedom or randomness. In a superdeterministic universe, the correlations we observe in Bell tests are not the result of signals travelling instantaneously between particles. They are the expression of a single, deeply structured initial state of reality. What we interpret as instantaneous influence is actually the unfolding of a pre-written correlation pattern that includes both the particles and the measurement devices, and even the decisions made by the scientists. This reframes everything. Instead of particles influencing each other across space in real time, there is only one connected history, unfolding in a way that makes separation appear real but not fundamental. The spooky aspect disappears, but at a profound cost. The cost is that independence itself becomes an illusion, and so the tension remains unresolved. Bell experiments, especially the modern loophole-free versions, show that local realism in its simplest form cannot explain the data. Something has to give. Either nature allows some form of non-local correlation that cannot be used for communication, or the deeper structure of reality includes correlations that extend across all events in the universe from the very beginning. What makes this so unsettling is that both explanations reproduce the same experimental facts. Both survive every test we have managed to design, and both describe radically different versions of reality. One preserves freedom of experimental choice, but introduces instantaneous connections across space. The other preserves locality, but removes the independence of choice itself. At the heart of it all is a single question that has never been experimentally settled in a direct way. When we perform a Bell test, are we truly probing independent aspects of reality? Or are we witnessing a universe so deeply interconnected from its origin that independence was never part of the story to begin with? Part 14. The deeper physics nobody can access yet. There is another possibility that sits underneath all of the interpretational debates, and it is the one that physicists often treat with a mixture of caution and fascination, because it does not try to reinterpret quantum mechanics, it tries to replace it. Instead of asking whether the strange correlations in Bell experiments come from non-locality, hidden variables, or superdeterministic pre-correlation, this view asks a more radical question. What if quantum mechanics itself is not fundamental at all? What if everything we associate with quantum weirdness, the entanglement correlations, the apparent collapse of the wave function, the probabilistic nature of a measurement, Even the discomfort we feel when we try to assign meaning to it is not a feature of reality at its deepest level, but a feature of our perspective on it. In this picture, quantum mechanics is not the bedrock. It is a kind of effective language, a statistical interface, a coarse-grained description of something deeper, the way temperature is not a property of individual molecules but a macroscopic summary of their motion. You never observe temperature in a single particle. You observe it when you lose track of the underlying details, and so the question becomes, is quantum mechanics similar? Are we mistaking a loss of microscopic information for a fundamental law of nature? This idea is not new. It traces back in spirit to Einstein himself, who was never comfortable with the idea that quantum mechanics represented the final word on physical reality. In the last decades of his life, he pursued a unified field theory, hoping to derive both electromagnetism and gravity from a deeper, more deterministic framework. He never succeeded, and history largely remembers that effort as a failure. But what is often overlooked is that the motivation behind it has never disappeared. It has only shifted into new mathematical languages and new research programs. Today, we know something Einstein only suspected. Quantum mechanics and general relativity do not fit together cleanly. Each works extremely well in its own domain, but when you push both into extreme regimes, very small distances, extremely high energies, or near singular gravitational fields, they stop agreeing with each other. The most famous scale where this breakdown becomes unavoidable is the Planck scale, around 1.6 times 10 to the minus 35 meters. At that scale, the energy required to probe structure approaches about 10 to the power of 19 giga-electron volts, far beyond anything we can currently produce or observe. What matters is not just that the numbers are extreme. It is that both theories begin to lose predictive meaning at the same time. Quantum mechanics assumes a fixed space-time background. General relativity makes space-time dynamic. When both are pushed to their limits, the assumptions underpinning each framework start to conflict. This tells us something important. At least one of them is incomplete. And possibly both are approximations of something deeper that does not separate quantum from geometry in the way we currently do. This is where speculation becomes scientifically motivated rather than purely philosophical. Because if there is a deeper theory, often called a theory of quantum gravity, then it must reduce to both quantum mechanics and general relativity in their respective domains. That means the familiar laws we use today would emerge as limiting cases, not fundamental truths. Just as Newtonian mechanics emerges from relativity when speeds are low compared to the speed of light, quantum mechanics and general relativity might both emerge from a more unified structure that looks completely different at its core. Several approaches to quantum gravity explore this possibility in different ways. Loop quantum gravity suggests that space itself is not continuous, but made of discrete quantized structures, like a network of fundamental loops. In such a picture, geometry is not a smooth backdrop, but a granular object that becomes smooth only at large scales. String theory takes a different route, proposing that the most fundamental entities are not particles at all, but one-dimensional strings whose vibrational states give rise to all known particles and forces. Causal set theory goes even further in rethinking space-time, suggesting that space-time is fundamentally a discrete ordering of events, where geometry emerges from causally related building blocks rather than existing as a continuous manifold. None of these theories is experimentally confirmed, and none has yet produced a definitive, testable deviation from standard quantum mechanics or general relativity at accessible energies. But what they share is a willingness to modify the structure of space-time itself at extremely small scales. And that is where things become interesting in relation to Bell's theorem and entanglement. Because if space-time is not smooth at the Planck scale, then the notion of distance itself may not be fundamental. What we perceive as spatial separation between entangled particles could be an emergent feature of a deeper connectivity that is not spatial in the usual sense. In such a framework, correlations that appear instantaneous might not be signals travelling faster than light through space. They might instead be expressions of a deeper structure in which the concept of travelling through space does not apply at all. From this perspective, the weirdness of quantum entanglement is not evidence that the universe violates relativity. It may be evidence that our concept of locality is incomplete. Locality assumes that objects are only directly influenced by their immediate surroundings in space. But if space itself is emergent, then locality might also be emergent. What looks like non-local influence could simply be what a more fundamental, pre-geometric system looks like when projected into the language of space-time. To make this more intuitive, imagine looking at a high-resolution painting through a very low-resolution screen. At low resolution, fine details disappear and patterns can appear disconnected or even chaotic. Lines that are smooth in the original image may look broken or discontinuous. Now imagine that all your measurements are done through that low-resolution screen. You might conclude that the image contains strange discontinuities or non-local jumps in structure. But the problem would not be the image itself. It would be your inability to resolve it properly. Quantum mechanics might be playing a similar role. It could be the low-resolution description of a reality that is fundamentally continuous, deterministic, or structured in a way we do not yet understand. Entanglement would then not be a mysterious instantaneous influence between distant particles. It would be the visible trace of underlying connections that are not constrained by spatial separation because space itself is not the deepest layer of reality. This is where the idea becomes both powerful and limited. It is powerful because it offers a way to dissolve the apparent paradox of faster-than-light correlations without violating relativity or introducing hidden conspiracies like superdeterminism. It suggests that the paradox arises only because we're using the wrong conceptual framework. But it is limited because at present it does not make clear, testable predictions that differ from standard quantum mechanics in experimentally accessible regimes. That is an important constraint. Despite decades of development, no quantum gravity theory has yet produced a confirmed experimental signature that would clearly indicate the underlying structure of space-time or modify quantum mechanical predictions in a detectable way. This means that, for now, the idea remains in the category of deeply motivated but unverified speculation. Still, the absence of experimental confirmation does not remove the motivation for the idea. It only highlights how deep the problem is. We know that quantum mechanics and general relativity cannot both be exact descriptions of nature at all scales. We know there must be a deeper framework that unifies them, and we know that whatever that framework is, it may radically reshape our understanding of space, time, and causality. If that is true, then what we currently interpret as non-locality in Bell experiments might not be a fundamental feature of reality at all. It might be a projection of a deeper structure that does not respect the same boundaries we impose on space-time. In that case, the universe is not necessarily sending influences faster than light. It might simply be operating on a level where the distinction between local and non-local has not yet become meaningful. And that leads to the central tension that connects everything back together. Whether we interpret Bell violations as evidence of instantaneous influence, pre-correlated initial conditions, or emergent structure from a deeper theory, we're always confronting the same underlying issue. Our current framework of physics may not be the final layer of description. The universe may not be breaking its rules. It may be revealing that the rules we think are fundamental are actually approximations. And if that is the case, then the strange behavior of entangled particles is not a paradox to be solved inside quantum mechanics. It is a clue pointing toward the theory we do not yet have. Part 15. The Unresolved Core Mystery. Let's take stock of where we actually are, because it is very easy to get lost in the layers of interpretation, philosophy and speculation that surround this topic. When you strip everything back to the hard core of experimental physics, what remains is already extraordinary enough that it barely fits comfortably inside our intuitive picture of reality. We know, with a level of certainty, that physics reserves for its most established results that quantum entanglement produces correlations between distant particles that cannot be explained by any theory that is both local and realistic. That is not a philosophical claim anymore. It is an experimental fact. This has been tested repeatedly across decades using increasingly sophisticated setups. Early experiments were suggestive but incomplete. Later experiments closed major technical gaps, and in the last decade, so-called loophole-free Bell tests removed the remaining serious experimental objections. Independent research groups in different countries, using different detection systems, different photon sources, different timing strategies, and different randomness methods, all observed the same underlying pattern: the correlations predicted by quantum mechanics and the violation of Bell inequalities that rule out local hidden variable explanations. The statistical strength of these results is not marginal. These are not almost violations or borderline anomalies. They're robust, repeatable, and consistent to levels of precision that in any other area of science would be considered definitive. This is part of why the 2022 Nobel Prize in Physics was awarded for work directly tied to Bell inequalities and entanglement experiments. The scientific community is not debating whether the effect exists. The effect is established. And what that effect says in its simplest form is deeply counterintuitive. Measurements performed on entangled particles show correlations that exceed the maximum possible limit allowed by any theory in which information is confined to travel at or below the speed of light, and in which particles carry pre-existing independent properties. In other words, if you try to build a picture of reality where particles have definite states in advance, and where no influence travels faster than light, you cannot reproduce what experiments actually show. Nature violates that combined assumption. At the same time, we also know something equally important and often misunderstood in popular discussions. These correlations cannot be used to transmit information faster than light. This is not an experimental limitation. It is a mathematical result known as the no-signaling theorem, embedded in the structure of quantum theory itself. What this means is subtle but crucial. If you measure one particle of an entangled pair, you instantly know something about the result of measuring the other. But you cannot control the outcome of your measurement in a way that encodes a message. The results are fundamentally random at the level of individual events. Only when you later compare data sets do the correlations become visible. So the universe is doing something very strange here. It produces correlations that look instantaneous across any distance you choose, but it simultaneously prevents those correlations from being used as a communication channel. The connection is real in the data, but inaccessible as a signal. This creates one of the most unusual structures in all of physics, a kind of non-locality that is experimentally visible but operationally silent. It shows up in statistics, not in messaging. It shapes correlations, not causation in the everyday sense. And this is where the central mystery begins to sharpen. Because once you accept that these correlations are real and experimentally established, the next question is unavoidable. What is producing them? This is where every major interpretation of quantum mechanics enters, and none of them come without a cost. The Copenhagen interpretation, historically the most widely taught, essentially refuses to answer the question in mechanical terms. It says the mathematics works, the predictions are correct, and the act of measurement produces outcomes, but it does not provide a physical story of what is happening between measurements. It is a framework for calculation, not explanation. Its strength is operational success. Its weakness is that it deliberately avoids describing an underlying reality. Many-worlds interpretation takes the opposite approach. It insists that the wave function never collapses. Instead, all possible outcomes occur, each in a branching, non-communicating segment of reality. This removes randomness at the fundamental level, but replaces it with a vast and ever-branching multiverse. The cost here is ontological. Reality becomes vastly larger and more structurally complex than anything directly observable. Bohmian mechanics offers another path. It introduces definite particle positions guided by a pilot wave that evolves according to quantum rules. This restores determinism and clarity at the level of particles, but it does so by introducing explicit non-locality. The guiding wave must coordinate distant particles instantaneously, which makes it difficult to reconcile cleanly with the relativistic structure of space-time. Then there is superdeterminism, which we discussed earlier in detail. It preserves locality by denying the independence of measurement choices, but in doing so, it forces us to reconsider the very foundation of experimental reasoning itself, since it implies that the apparent freedom of experimental setup is part of a pre-established global correlation structure. And beyond all of these, there are speculative extensions like quantum gravity approaches, which suggest that both space-time and quantum mechanics might emerge from a deeper underlying structure that is not yet fully understood. But these remain unconfirmed. Each interpretation preserves the experimental facts while changing something fundamental about how we understand reality. That is the key point. None of them change what we observe. They change what we think observation means. Einstein was right to be disturbed by this, even if his preferred resolution, local hidden variables, does not survive experimental testing in its simplest form. His discomfort was not about calculation. Quantum mechanics is arguably the most precisely tested theory in the history of science, accurate to extraordinary levels of precision. His discomfort was about meaning, about what kind of world could possibly produce these results. The modern physics community, in a sense, has adapted by separating the formalism from interpretation. The equations are used as tools. They predict outcomes with extraordinary accuracy. They guide technologies ranging from semiconductors to quantum computing. But the question of what the equations are describing physically has become optional in practice. It is discussed, but not required for doing successful physics. Bell's theorem stands as the permanent dividing line in this story. It is not just a technical result, it is a constraint on reality itself. It tells us that any theory that tries to preserve both locality and realism cannot match the observed world. That boundary is not going away. It has been tested, refined, and strengthened over time, not weakened. So what remains is not uncertainty about the data. The data is solid. What remains is uncertainty about ontology, about what kind of reality is capable of generating that data. And here is where the situation becomes genuinely unsettling if you sit with it long enough. We are not debating whether entanglement exists. We are not debating whether Bell inequalities are violated. We are not debating whether local hidden variable theories work. All of that has already been settled. What we are debating is something much deeper. What reality must be like in order for those settled facts to be true? And the options that remain are not small adjustments to a familiar picture of the world. They are fundamentally different visions of existence. A universe that branches endlessly into parallel outcomes. A universe in which distant events are connected by instantaneous coordination that cannot carry information. A universe in which every experimental choice was encoded in the initial conditions of everything that followed. Or a universe in which both space-time and quantum mechanics emerge from a deeper structure we have not yet uncovered. None of these are comfortable in the way classical physics once was. Each replaces one mystery with another. Each preserves the data while changing the meaning of reality itself. Einstein's ghost, metaphorically speaking, sits at the beginning of this story, recognizing the tension before the mathematics fully exposed it. Bell's theorem sits at the center, formalizing the boundary between classical intuition and quantum reality. And the experimental results sit everywhere, repeating the same message with relentless consistency. Something in nature produces correlations that no local classical story can reproduce. We have done what physics always strives to do. We have measured carefully. We have tested repeatedly. We have removed loopholes. We have refined the experiments to extraordinary precision. And still, the same picture remains. Something happens between distant particles that cannot be described as a signal, cannot be described as a classical influence, and cannot be explained by local hidden properties alone. We know exactly what the phenomenon does. We can predict it. We can measure it. We can use it in technology. But when we ask what it actually is, when we try to translate the mathematics back into a story about reality itself, the answers diverge into interpretations that are radically different from one another, and none of them can yet be confirmed as the final one. And that is the final uncomfortable position we're left in. We know what happens, we don't know what it is.